Good morning, this is Lois Gray, North Island College. So this is week 11 of the Control and Instrumentation class, second last week. So today we're just going to look at flow and depth, so some senses for flow, a little bit about Bernoulli's equation, and a little bit about how to measure depth. We kind of touched this already, so most of this will be quite easy and familiar to you, I think. Maybe some of the senses you might not have seen. So has anybody any questions from last week, first of all? So we did quite a lot last week. We did temperature, displacement, and velocity, I think, and then also force, pressure, and acceleration. No questions. What about the coursework? Is everybody getting on okay with the coursework? Yeah, you finished? Yeah.
Almost.
Yeah. Okay, so it doesn't seem to be too much problems. I think because I gave you an example file, that's probably helped a lot. Well, that's fine. Right, so I'll just switch over. I'll go through the slides. I have a little online, what they call learning object thing to go through, and then that's about it. So it'll be quite short, maybe less than an hour today, I would think of that.
Perfect.
Yeah. Have you guys got enough to do? I suppose we've got other things to do. There's always self-assessment questions for each week that you can go through anyway. Okay, so let's switch over to the notes. So just so you know where we are, we're learning resources instrumentation, week 4 of instrumentation, which is week 11 of the course. This one's following the schedule. The principal's class isn't following the schedule very well. Right, that's dark enough, I think. I'm going to sleep. So I've just got some slides. Slides are here. So this is a bit more of a mechanical subject, and it's not my best subject, so if I get stuck, I'll maybe ask mechanical people to help me, which is probably you, Sergio. You're the only one. Some years there's more mechanical than electrical, it's odd. Other years there isn't. There seems to be a balance. Right, so we're talking about flow. You probably already know this. There's two really definitions of flow. You can either have laminar flow, which is what probably most of us consider to be flow, where things are moving quite smoothly through the medium. The atoms are all moving quite smoothly, and it's got a Reynolds number of less than 2,300. And then you've also got turbulent flow. So the rig downstairs, I don't know, have you used the rig downstairs to look at that? Yeah. So you can make the rig downstairs show you laminar flow or turbulent flow. You can inject and dye. And obviously turbulent flow just means the particles are kind of inside the fluid are moving around in a more random kind of manner. And you can see that sort of turbulence in the water. It's just like what it sounds. And that's with a Reynolds number of greater than 2,300. And the Reynolds number is directly proportional to the velocity, the diameter of the pipe that is flowing through, the density of the fluid, which is that symbol rho, that little P sign, and the viscosity of the fluid, which is mu. Is that always mu? Is that the right symbol? Viscosity? I didn't think it was.
No.
No, it's not, is it? It's something else normally. Okay, I don't know where I got that from. You might see that as a different symbol, that mu thing. But anyway, just out of interest, viscosity and density are not related to each other. Some people might think like a dense fluid is always going to be more viscous, or vice versa, but you can quickly remember that by thinking of oil. So if you think about oil and water, if you pour them both, obviously the oil is going to flow more slowly. So it's quite a viscous type of material or liquid, whereas the water is going to flow quite fast. But then again, if you mix oil and water, what happens to the oil? If you mix oil and water, it sits on the top, so it's obviously less dense, yeah? So that's a good way to remember that there's not really a relationship between density and viscosity. It doesn't follow that because something's dense, it won't be it'll be more viscous. Because oil's a good example of something that doesn't meet that sort of thing. Okay, so talking about Bernoulli's theorem, mechanical people again will know loads about this already. So the idea is that energy is conserved. So if you move a volume of water or liquid in a pipe from one height to a different height from a wider diameter to a smaller diameter, you're always conserving the energy. So we can derive Bernoulli's theorem, which basically works on that principle. Of course, we're all going to be talking about laminar flow, mostly. We're not really interested in turbulent flow. I guess if you've got to measure turbulent flow, you might need to use some slightly different instrumentation. And we're also talking about incompressible fluids, so that's things that you can't actually make smaller by compressing. They stay the same size. So you've got that equation where you have potential energy. What's potential energy related to? You've got choice, velocity, height or pressure?
Height.
Height, yeah. Okay. Pressure energy is obviously pressure. Kinetic energy is obviously velocity, speed. Stays constant. So if we go back to that slide, the energy here will be the same as the energy up there. Yeah, so we end up with an equation like that, but that's a bit unusual. I think I might just go through the one I've got in my notes here. I don't know if I've seen that one before. So it was down. So you can actually derive Bernoulli's formula. There's a few different forms of it. That's one form, but more useful one. So you've got the pressure energy. Oh, that's just in terms of energy. Pressure energy plus potential energy plus kinetic energy. So pressure energy is like force times distance. Yeah, that's what we'd give you for that. So force times distance. And if you think of a little bit of fluid in a pipe here, if it's got cross-sectional area A and it moves that distance, then the volume of that little bit of liquid is area times distance, isn't it? So we can rewrite that as distance equals velocity over area. Is that right? Equals area times distance. Have I done that right? Volume equals area times distance. Yeah, that's right. Yes, you could rewrite that force. So that's one equation. And then the second one is that pressure equals force over area. So you can change that F to being that P, F to being force over area. I think I've done that wrong. I've done wrong. Volume equals area times distance. Yeah. So to get rid of the area, you can write that like that, yeah? Force over area times area just gives you force. Then you've got the distance, which is oh, yeah, that is right. Sorry, volume over area. Yeah. So this is all just to do with this first term here. Right. Then we got the. Let's do this. Got potential energy, which we're used to seeing as mass times gravity times height. Most people know that. Yeah. And then we've got kinetic energy. Anybody know the equation for kinetic energy?
Half mv squared.
Yeah, right. So we've got the last one. And where v is velocity this time, so I'll write it like a wee u. And that's volume, that's velocity. So the little green thing's velocity, the big black one's volume. So then we can rewrite that. These a's will cancel out. Force over area is pressure, so that's pressure times volume plus mgh. I should have done it in red, but never mind. That's a half mv squared. This is all to do just with the energy on one side, yeah? So let's say the energy in, pressure in, volume, the volume stays the same. So it doesn't really matter whether you're talking about the volume coming in or the volume going out, so we'll leave that. height of the input and velocity at the input. And then the other thing we know that is that density is mass over volume. So rho equals mass over volume. So we can replace the volume, the mass parts with rho over v. So you end up with E1 plus rho g H1 plus a half rho E1 squared. So you can do that derivation. You don't really need to learn that though. But anyway, so that's on one side, and then you've got the same on the other side, and that's Bernoulli's theorem essentially. So your equations, in fact, we've type here. Due to energy conservation, if that's the input and that's the output, you've got pressure in plus density times gravity times the height at the input, because obviously there's a change in height, yeah, plus a half rho v squared at the input equals the same at the output, yeah? Pressure out plus rho g h out plus a half rho v out squared. And that's Bernoulli's formula. And that's kind of the, I don't know, it's the basis on which the instrumentation for sort of flow is based, because quite often you'll be looking for a pressure difference. I'll explain that a bit better in a minute as well. Oh, right, yeah, you know more about that anyway, won't you? You'll have done loads of this stuff. But, so you can ignore that equation just now. I don't know how right that is. But I think it's the same equation, it's just they've used weight instead of mass and volume and things. Okay, so it also applies to slow-moving gases, but there has to be below a certain speed, a Mach number less than 0.2. I can't exactly remember what Mach number is. It's something a bit new. Yeah, speed of sound in gas. That's 1 Mach. Oh, sorry. Anyway, we don't really need to know too much about this stuff. It's just explaining the units that are used. Pressure's measured in newtons per metre squared. That's the same whether it's liquid or just general pressure. We know that already. This little symbol here is gas density, and that big symbol is, so air has a density of 1.4. So that's just to do with how many atoms there are in a certain volume of gas. Yeah, that's what when you're talking about density, you're always talking about number of atoms in a given area, yeah. Okay, so we don't really need to care about that. We also don't really need this. I'm not very sure why all this stuff is in the slides, but just so you're aware that Bernoulli's formula is only applying to laminar flow, slow speed, so Mach number less than, I think it was 0.2 or something, yeah. And no friction, okay? So no friction, but of course there usually is friction. And if there is friction in the pipe, then you have to add this Darcy formula. So people who are doing sort of, I suppose, ventilation systems or cooling systems probably have to take all this stuff into account. But for this course, you don't really need to do that because you're not expected to be designing flow systems, just instrumentation for them. Really. So there's a bit of friction, and you obviously just need to add that into the formula as to the total energy. That's in the. I've just passed through that. I don't think we need to know too much about that. But what's really interesting about Bernoulli's principle, and it might not be instantly obvious, is that a fluid flows faster in a smaller diameter than it does in a larger diameter. Yeah, so that's kind of counterintuitive. I think most people would think it would flow faster in the bigger pipe because you think, oh, there's more area for it, it can go quicker. But that's not true. It flows faster in the smaller area. And because it flows faster in the smaller area, and because of the energy conservation thing, that also means that the pressure drops in the smaller pipe and increases. And again, that's kind of counter. You wouldn't expect that, I don't think. Well, I wouldn't expect that. But that is what happens. So that's how a lot of these flow measuring instruments work, because you can put a small sort of constriction in the flow, and you can measure the pressure difference between the large area and the small area, and you get a very accurate representation of the flow. P1's velocity 1, P2's velocity 2, P1 pressure 1, P2 pressure 2. So that's just explaining what I just said. And the next bit. So you'll have seen these, like there are differential pressure meters and things like that. I'm sure that there's probably loads of these at Doonray, because a lot of what you're doing is to do with flow. Uses this sort of thing. So there's lots of different ways. You've got your electronic differential pressure cells, you've got your manometers, which you can just look at. You've got, what else have we got? Well, there's other ways of putting the restriction in. There's things like orifice plates and stuff like that. I've got quite a good little slide thing about that anyway. There's these Pitot tubes. These were used in airplanes quite a lot in the past. So it's just the same idea. I'm using two different diameters to measure, measuring the pressure between them. I think there was a plane crashed in South America. They reckon it was because these Pitot tubes froze up, so the airflow couldn't go through them. That's still the same idea. You can rearrange Bernoulli's formula to get this sort of equation here, where the velocity squared is equal. Is that velocity squared or is that volume? That's the difference in velocity between the two pressure areas. So that's the difference in velocity squared is equal to 2 times the difference in pressure over the density. Rho. Sorry, over the, rho's not density, what's rho? Is it density? Sorry, it is density, yeah. That's right, I was right, yeah. Okay, so that's a typical manometer type of one. I don't know if anybody's ever seen them. I'm guessing they're quite old-fashioned now. We used to have some of these downstairs. I used to bring them up, but they've been thrown out now because nobody used them. So you can see how you can measure pressure difference there. I've got a better thing for showing you. So this is just telling you that there's a direct relationship between the flow rate, Q, and the pressure, or the difference in pressure. And that K is related to the constants, to do with the pipe diameters and things like that. Right. And this is talking about volumetric flow. I'll talk about that as well. There's some other methods of defining flow. Probably the most common is volumetric flow. So that's amount of volume passing every second. But you have different instruments for measuring different types of flow. So I think I'll show you the wee thing now, because the little RLO thing, because it's more interactive than this and a bit more interesting. Does anybody have any questions about any of those? No. Quite straightforward, isn't it? Okay. Straightforward, but you need to remember. So this is just one of these Wisconsin online things, which I always think are quite good. I should say, if you've got any problems with any subject and you want a wee bit more, maybe visual information, the WISC Online, WISC Online, is quite good. They've made loads of these little reusable learning objects, they call them. I think they're quite good for learning, because they've got good pictures and things to show you what's going on. So just a wee bit about flow there. We're talking about fluids, but they could be gases or liquids. Yes, the definition of fluid includes gases as well. The thing that causes flow is obviously a high pressure to a low pressure. You don't get any flow if there's no pressure. Now the pressure could be something like a pump pushing the fluid through, or it could be gravity. Gravity also gives you a pressure. Yeah, but you won't get any flow if there's not a pressure of some kind being applied. So that's just a wee thing, that's just what I just said. It could be either pressure from a pump, or it could be gravity, which also is pressure. So obviously you need to measure flow quite a lot for loads of things, everything from sort of your car cooling system to your big process industries, pipelines, oil pipelines, what's the flow rate through them. Mostly I've been involved with cooling units, so that's the thing I'm most aware of, but there's obviously a lot of other fluids flow as well besides just cooling fluids. So we've got all these different types of measurements. Like I was saying, there's different types of flows. You've got absolute quantities, which doesn't bother about time, it's just measuring a volume flowing from one side to another. You've got percentage flow rate, which is what it says, it's percentage compared to our normal flow rate. Volumetric flow rate, which is the one we looked at, which is volume per second or volume per minute or whatever. And then you've got mass flow rate, which is mass per minute or mass per second. Okay. So you've got different instruments depending on what you're measuring. Did you know that you had different measurements? That's something you've come across before? No? Okay. So you've got absolute ones, are quite straightforward. You just fill up a quantity and then release it, and you know how much has flowed if you do that. So that's the absolute ones. And the rest are based on the rate of time, or use time as well. So it's quite straightforward. If you're doing the absolute quantities, you can fill up a tank and then discharging it to another location, and you know how much you've discharged, yeah? And there's quite a lot of flow meters work on that principle. I think the ones you have for your gas in your house and things like that do work on the same principle. So this one does, it fills up this volume here and then discharges it through there, and you can obviously measure that volume, or you know what that volume is. Same with that one as well, it's also doing the same thing. It's a specific volume coming in here and then going in there. And that's just the same idea with a piston. So like I said, these are quite common, I think, for gas measurements, but maybe not so much for liquids. Just got some applications there, measuring quantity of additives to add, or transferring something between two tanks. Obviously you don't want the second tank to overflow, so you need to know how much you're actually putting into the next tank. And then the other way, which is probably more common, is measuring over a period of time. I think this must be American, because I don't think we use gallons per minute or cubic feet per minute. We probably use meters cubed or millimeters cubed per minute or per second. So, but obviously there's a whole range of different measurements. Depends what you're talking about. So some applications prevent a high flow rate. It could also be to assure a specific flow rate, as I say, again, for cooling. Anyway, you know what flow meters are for. So this is another way of doing it with the pressure, yeah? So again, you've got fluid coming in, and then you're making it flow for a smaller diameter, so you can measure a pressure difference there. The more common one is venturi tube. I suppose orifice plates are quite common as well. The nice thing about an orifice plate is it doesn't require a length of pipe. It's just something you can just insert into the pipe, which is good. The disadvantage, of course, of these sort of things is that you have to actually access the fluid. So, of course, if it's a contaminated fluid or a corrosive fluid, these methods are not so good, because you're going to have to actually insert the flow meter into the fluid. There are other ways which don't involve contact, which are a bit better. They do depend on the type of fluids. You've got your electromagnetic flow meters, which will just use magnets to measure the magnetic fluid passing through. Or you can have two magnets, one at each side, and they can measure when the fluid passes one bit and when it passes another. But the problem with them, of course, is you need a specific type of fluid to do that. You need like a magnetic fluid. So I suppose these are more common. Oh, sorry, I didn't mean to do that. These are all working on the pressure. Bernoulli's principle theorem. You'll have seen these ones downstairs, possibly, the rotometers. Yeah, they're just a visual display. So what happens is the water or liquid moves up and down due to the pressure again in that, and you can measure the flow rate based on the height. Obviously, more pressure pushes it higher, and less pressure pushes it lower. So the other way is to measure, as I say, as percentage, so you can tell if a pressure has dropped or risen quite quickly by looking at the percentage flow rate. So again, this is in gallons per minute, which is a bit odd. But so if you set your reference, and then you can measure compared to that. So this one's measuring 50% would be 250 gallons per minute. I think that's straightforward. No question there, I don't imagine. And then the other way, the other type that's used is mass flow rate ones. So they're based on the weight of material. Yeah. Oh yeah, this is quite a good one, the Coriolis meter. This is quite a nice one, because you can use this for like quite dense fluids or quite viscous fluids or really easy flowing fluids. And what happens there is that there's a kind of twist introduced. Once something starts to flow through it, I think I might have a wee video of this actually, there's a sort of twist introduced. And the twist is proportional to the speed of the liquid flowing through it. So you can use some sensors to detect how much that's twisting and measure it over time. I think the video will show it better. And that will give you an indication of how fast it's flowing. And then there's also, if you just look at if you just set it vibrating and you look at the frequency it vibrates at, that also gives you a measurement of the density of the fluid as well. So, or is it the viscosity? I'm not sure. I always get them confused. But let's see if I've got the video. This is all in your notes anyway, so you can play these yourselves. So. This one is quite a nice video. This is from Enders and Hauser, who are a quite well-known manufacturer of. I'm not sure if the sound will work, but you can see the pictures. So. Don't think you need the sound, you can just see it without the sound. You play it yourselves with the sound later. That's just an introduction. All the different things you might want to measure. So you'll have seen these. You see these quite a lot. These types of flow meters are quite common. Do you want the sound on? It's a bit odd without the sound. I'll try putting the sound on. Are you okay with just watching it?
We get a picture.
Yeah, it's more just so you can see what's actually going on. So what they do is they set that to vibrate, or to not to vibrate, to oscillate a wee bit like that. So that wee thing that's firing the pulses there is just making that do that. And you can see when there's no flow, if you set some sensors to detect the sort of twist, they just flash and line with each other. But as soon as you get some flow, the pipe starts to sort of wiggle, and then you get a difference between when of these are detecting it, and you can measure the time difference. And that will be proportional to the speed at which the fluid's flowing. It's quite clever. And it's all to do with the Earth turning and gravity, the reason that happens. Of course, it all happens inside the instrument. You don't really need to worry about what's going on. But if you're just interested in fluid density, you can just do a measurement like this, without having it flow. And the speed at which it oscillates will be dependent. Obviously, the more dense it is, it will oscillate less quickly. So that's another method. You can make both of the measurements at the same time, but I'm guessing you'd have to stop the fluid from flowing to do the second one. That's enough of that, I think. Okay, and then some other methods. You've got things like your turbine wheels. Again, you've probably seen them in various systems, I don't know. But the principle of that is just a little turbine. It turns proportional to the speed at which the fluid's going through it. So you can detect how many rotations it does in a certain amount of time, or you can measure the time for one rotation, and that would give you the flow again. We've got some of them downstairs. We use them downstairs quite a lot. The disadvantage of that, obviously, is you've got moving parts in a liquid. And again, if it's a corrosive liquid, it's not going to last very long. But you've got the positive displacement type. That's the one we looked at the beginning. Ultrasonic ones, they're probably pretty common. They're nice because they don't actually go in the tube, in the liquid. They're fitted on the outside of the liquid, so they don't involve any requirement to cut open the pipe. You can just fit them. And all they're doing is they're just going to... the ultrasonic waves bounce off the sort of atoms in the fluid, and you can measure the difference between detecting them here and then detecting them there, and that's obviously proportional to how fast they move through. They're used quite a lot. I was telling you about Hoy Pumping Station. They use a lot of those ultrasonic ones. They also use ultrasonics for depth as well, depth sensing. That's the Coriolis one that we just looked at. That's a similar type anyway. And that's the electromagnetic one I was talking about. But you do need a fluid that's got some magnetic qualities to use that one. Okay, so that was all on flow. Was there any questions? Anybody come across any other types of flow meters? No? Not with where you worked, you might have seen some others. What's the most common kind?
Pitot Tube and Pitot Tube and different problem.
Is it? Right.
Yeah.
Oh, okay. Yeah. I thought it might have been the Coriolis ones. No.
Never seen one of them.
Never seen one of them. Right. Okay. Because they're one of the more reliable ones and more accurate as well.
Also manometers as well.
Yeah, I'd imagine manometers are probably quite common. Yeah, because most of what you're doing is measuring on the spot, isn't it? Really, you're not really automatically. Well, I suppose you can use an automatic sensor with a manometer as well, but you'd have to detect level. You'd have to do a combination of level and flow. So ways of measuring level, probably the most common is ultrasound. Even nowadays, they used to be quite expensive, but nowadays they're actually quite cheap. I think even some students were buying them last year for projects. So, they're only about £30-40 for a reasonable one, so this is a pretty common way of doing it. What's nice about that, again, is there's no contact between the meter and the fluid. So again, you've got a lot. That's quite a big advantage, I guess. And they're also quite accurate as well. I'm not sure how good they are if the fluid's very turbulent. So I think if there's a lot of spray or turbulence, they sometimes can give you a false reading. And I'm also not very sure if they're very good with sort of fluids that are quite gassy, because I think sometimes they can bounce off the wrong thing. And also solids, I mean, they're used in silos and things like that as well, but I guess it might depend a wee bit on what the actual material is that they're measuring as to how good it would be. So obviously the idea of that is it just bounces. Send the ultrasound signal, it hits the surface of the thing you're trying to measure, bounces back, and you can measure the time it takes to do that. Similar to a sort of radar type idea. Pretty easy, really. That's just the equation there. So the time is 2 times the distance divided by the speed of sound, because it's ultrasonic in sound. And they've got capacitor methods. These are also quite common, especially with metal tanks. Because what you can do is just have a single capacitive probe, a single conductive probe, and you can use that and the tank as the capacitor plates. And then obviously as the tank fills up and empties, the dielectric is this part here, and that changes And so the capacitive change, because the dielectric of the material will be different from the dielectric of air, dielectric constant of air, so you'll get a difference in capacitance as it rises and falls. So that's quite common. Another way I've seen them is where you've actually got two plates in a sort of plastic tank. I think that might be the way they work in your car petrol tank. But does anybody know? That's what car petrol tank uses. It's quite an accurate way of doing it. Nobody know? Nobody sort of do any mechanics on their own cars? No? All right, fair enough. And then I mentioned these Hall effect transducers before. So we used to have a tank from Vulcan which used these. And basically what happens then is as you bring a magnet, it's kind of like magnetic, I suppose. As you bring a magnet towards the material, these charges in the material are displaced. So when you put a current through that, it'll kind of, a bit like the Coriolis tube, will kind of bend and wiggle. The current will actually be pushed either to the bottom or pulled up to the top. And then that produces a voltage across the material as well. So you can measure the voltage, which is what's happening here. So again, I used to have a little picture that showed you that, but I think that's gone. You can look those up anyway. The way the level thing used to work, it came from Vulcan, is you used to have a whole load of these little sensors all the way up, and then you put a magnet inside the tank, and as the magnet went up and down, it triggered a sensor one at a time. And what was nice about that, you could use it in explosive environments and things, because there was no contact and no sparking or anything. The magnet was just going up and down by itself, and then these things were detecting. There was no contact between them in any way, so that was quite good. It was designed specifically for that, I think. Oh, okay, that's all there was for today. There wasn't too much today. Did you go through the questions last week? No. Well, maybe just do that, because I think last week's questions are quite important. If you want to just hang around for a minute. So that was... I'll get this through that in a minute. I had to rewrite them last week, actually, because I deleted them by mistake. So I hope you appreciate that. So what we were on?
No.
We did those ones. Oh, the temperature ones are.
Out of order.
Oh, temperature there. I'm going to quick look through these. I'm not going to do the calculation ones.
No.
I'm not going to do the calculation ones, we can just the other ones. So what physical parameters can a rotary shaft encoder measure?
Angular speed.
You measure speed. You measure anything else? Yeah. Anything else? You can measure direction if you've got enough slots on it, yeah? Yeah, okay, so we go with direction as well. I think that's right. You can see in a minute. Which is a linear temperature response?
TRT.
Yeah, and probably this one as well.
Yeah.
I would imagine. These two definitely not.
No, they're definitely not. I have millivolts in it.
Yeah, what can you measure with an LVDT?
Still good.
Amplitude.
Or how do you measure with an LVDT? So you measure displacement, but what do you use for that? So that's the thing with the transformer, with the coil that moves up and down to change the transformer ratios. Phase definitely, and probably amplitude. Yeah, because as the coupling gets bigger and smaller, the amplitude coming out will get bigger and smaller as well. Yeah, so amplitude, I think that's right. I'll not do the calculation ones, you can have a look at those yourself. Yeah, we'll just give them a miss, I think. So do make sure you do them, because these are the sort of things you'll get in the exam, yeah?
In the exam is all of the calculations are electrical ones.
That's an exam, that one.
No, most of them are controlled. There's 70% control, 30% instrumentation.
Right.
But you mean like there's a Bernoulli'S formula? There might be Bernoulli'S formula.
Is there? Is there a listener?
I can't tell. Right, so you got that one right, got that one right, got that one right. I would imagine you would get these ones show you how to do the calculations if you can't do that. I'd certainly make sure you can do the electrical calculation. Because even if there is a Bernoulli's formula, it's only going to be one question. Yeah. Instrumentation is quite an electrical subject.
Oh.
Yeah.
Okay, do you want to see the other ones, or are you not really bothered?
Yeah, just go on.
Will I go through the other one as well, yeah?
Oh, aye. It's very long. Hysteresis.
So the other one you did last week was this one, I think? Loss pressure and... I think a lot of these ones are calculation ones, though. Make sure you can do that one, guys.
Aye, it was on practice ones months ago, you know what I mean?
Was it? Right, yeah. Okay, I've forgotten what the formula is. I think it's 1 plus 2 Rg over Ra gives you the gain. Okay, and then the common mode gain is always 1 for these type of amplifiers. So you can work out your common mode rejection ratio just by the gain that you calculated divided by 1, which is obviously just the gain you calculated, and 20 times the log of that gives you a common mode rejection ratio in decibels. So you can see that later. Right, why is an instrumentation amplifier better than a normal amplifier? So there's a few choices here. There's a few answers as well. So common mode rejection ratio, higher or lower? What's better?
Higher.
Higher, yeah, good. Was that just a guess?
No, I know
Yeah, what about input impedance? Do you want the input impedance to be higher or lower?
that. Lower impedance.
Lower.
Is it?
No, the answer's higher. If you think about it, if you have a lower input impedance, that's the same as a lower resistance, yeah? So then that's going to load your input signal more. Yeah, what you want is you want that to be a really high resistance so that it doesn't have any effect on the input coming in. So that's definitely higher. That should be higher.
It's got a lower offset voltage.
Yeah, that's definitely right, because offset's bad. We all know about offset. Yeah, you had a big offset in your coursework. Yeah,
Don't talk
your
to
negative offset. What about open loop gain? You can probably guess that one.
Lower.
No, actually higher. Okay, the higher your gain, the bigger range of signals you can take in, the more bandwidth you can use. Okay, so that one's higher as well. But that's fine. You're here to learn. You're not expected to know all the answers. What's absolute pressure?
It's pressure with respect to atmospheric pressure.
You sure?
Third one, is it?
The second one.
Absolute.
Yeah, you're right. It's the second one. Absolute's measured with respect to 0. Yeah.
Is that second
Ah,
one?
Gauge is
pressure.
the third one. No, sorry, gauge is that one, atmospheric, and then these two would be differential, I think. So it's this second one, yeah. Okay. I'll not do the calculations, as I said, you can look at them yourself. Yeah, these ones you have to look at yourself. They're all calculation ones. Now the pressure unit, meaning newtons per square metre, everybody should know this one. Pascals, yeah, that's the SI unit. So make sure you go look at the calculation ones. Just because I'm not going through them doesn't mean they're not important. I had it the wrong way around. It's 1 plus 2 Ra over Rg. I would memorise that if I was you.
Okay. Good advice.
Right. Yeah, that one we talked about already.
What was that again? Question 1 on what's this called?
The instrumentation amplifiers. Question 1's an instrumentation amplifier.
All right.
Right. Yeah, we got that right.
Do it. If you get it wrong, it's
Got that right. And then the other ones are all calculations, so you can work them out for yourself. Okay, I think that's probably enough. You want any more information? Right. No. Anybody got any questions?
Yeah, sure.
Okay, well, you can get back to doing your coursework, and you can have a look at these questions as well. And there's some for this week too.
I know that I'm going to do it as well.
This call has been disconnected. Thank you for joining.